So it's really a pleasure to be here. Thank you to the Carver Project for having me and to the department for having me give a colloquium. It's really been a wonderful visit and I've very much enjoyed myself. So thanks to both organizations. And as Doug said, St. Louis is a very interesting city for the intersection of science and faith because of St. Louis University and James B. McIlwain, who was a Jesuit priest who essentially really developed the seismological network inherited, initially it's called the Jesuit Seismological Network, and made it into a real scientific network for earthquake monitoring and analysis. He wrote a classic textbook on seismology. He was commissioned by the Air Force to participate in several important committees in the late 1950s during the International Geophysical Year, and he was elected the president of the American Geophysical Union a few years before his death. And yet, when you look at his depiction on the medal that the AGU gives its winners, there's no indication that he's actually a Catholic priest. His Roman collar has mysteriously disappeared. And when you read his biography, the AGU biography, description of him, his scientific accomplishments are clearly there, but there's no mention that he was actually a Jesuit priest. And I think this illustrates some of the tension that we have in our society today about the role of religious faith and the idea that maybe science and scientific discovery is replacing religion or taking a large part of the role of religion. How many of you in the audience have maybe had a discussion or an encounter with a friend or someone else who maybe was surprised, if you happen to be a scientist, that you're a scientist and you also are a practicing Christian, so I can raise my hand. And so this I think illustrates some of the tension. And so about 10 years ago I became interested in this question, and that led in part to my co-founding of the Society of Catholic Scientists with Stephen Barr, who was the director of the Bartol Institute at University of Delaware and is now retired. But it also led me to look at the biographies of scientists who also were overtly religious, and Catholic priests are a very good example of that. And the premier example of that, I would argue, is the person I'm going to talk about this evening, and that is Georges Lemaître. And so in order to use the slides, I'm going to put this away, and I'm going to talk to the microphone. So I'm going to give you his biography, and I'm going to both explain the science that he did in his time, which was the early to mid-20th century, the contributions he made, some of the adventures that he had along the way of recognition and lack of recognition from his peers, and also his particular views from a religious point of view of the role of God in the evolution of the universe, how we should regard the Bible, and the question of science and faith as two different ways of looking at and understanding our existence. So a very brief summary biography of him is here. He was born in Charleroi, Belgium at the very end of the 19th century. He served in the Belgian army in World War I and was decorated for being wounded. He then, after being discharged honorably from the military, he earned a master's in math in Louvain in 1922. He knew from the time he was a teenager that he was going to be a priest. And so he, during that period, went into formation to be a priest, and he was ordained in 1923. He was a diocesan priest. He was not a member of any religious order. He then petitioned his superiors to be able to continue his studies, and they agreed to that. And so after a brief time at Cambridge University in the UK, where he worked with Arthur Eddington, he enrolled in the PhD program in physics at MIT and actually did most of his work at Harvard, at the Harvard College Observatory. Interestingly, at the time, Harvard did not grant PhDs in astronomy, and that's why he had to go to MIT. But he worked with Harlow Shapley. He then got his PhD. He went and became a professor at Louvain, and he did that for his entire life. But he won several prizes, one of which, the Franck Prize in 1934, for which he's nominated by Einstein, was at the time the second most lucrative prize after the Nobel Prize. Of course, he couldn't keep it himself personally, but he donated most of it to the university. And then he was awarded the Eddington Medal of the Royal Astronomical Society. He was elected to the Pontifical Academy of Sciences, which is an honorific organization, which, by the way, you don't have to be Catholic to be elected to. Stephen Hawking was a member of the Pontifical Academy. He became its president in 1960, and he died in 1966. So sounds like a pretty typical, with the exception of the ordained part, pretty typical kind of professorial trajectory. But he lived at a very, very interesting time in modern astronomy. And it was an opportunity, living at that time, if you understood the theory of general relativity, to revolutionize our view of the universe, which is what he did. So this is a beautiful view from James Webb Space Telescope of galaxies scattered through the cosmos. We know today that those galaxies are collections, self-gravitating collections of stars, the bigger ones, hundreds of billions of stars in each galaxy, and we live in one of those galaxies, which we call the Milky Way galaxy, a spiral galaxy. But in the early 20th century, it was not understood that, in fact, the universe was composed of these large numbers of galaxies. It was thought instead, in the late 19th century and on to about 1920, that the Milky Way galaxy was the universe. In fact, if you read Arthur C. Clarke's early science fiction stories from the 1930s, he uses the archaic term for galaxies, island universes, because at the time, the Milky Way, up until the 1920s, was thought to be the universe. And these spiral features were thought to be clouds of gas within our own galaxy. So the picture on the left-hand side is from 1899. It's the Andromeda galaxy, but it was called the Andromeda Nebula at the time, nebula being the Latin for cloud. And the stars that you see in that picture are stars in the foreground. They're in our galaxy. The Andromeda galaxy is millions of light years away, but they didn't know that at the time. And if you come up and look at that picture, you cannot see any stars in the Andromeda galaxy itself. It was not until the 100-inch telescope was completed at Mount Wilson in California, about a decade and a half after the Lick Observatory picture, that astronomers could take pictures of nearby galaxies and see that they contained stars. And in fact, some of those stars gave clues to the distances to those galaxies. And there's a picture of me about a month ago at the 100-inch telescope, which is still there on Mount Wilson. It's no longer used for astronomical research. It's used for public viewing and music concerts. It turns out that with the shutter open like that, it makes a beautiful band shell and the acoustics are great. But I actually had the privilege of using that telescope in 1982 as a graduate student, working with someone who was at JPL, John Trauger. And it is truly an archaic masterpiece. It's a masterpiece of engineering, but it's definitely over 100 years old. So in the early 20th century then, without knowing that there were galaxies scattered through space, without knowing that the universe was expanding, which we know today, it was assumed to be static and eternal. And at that time, in 1917, in fact, Albert Einstein published his theory of gravity, which we call the theory of general relativity, which says that space is curved, and that curvature is caused by the material, the matter in the universe. And furthermore, that matter, the more material you have, the more space is curved. So the theory is incredibly beautiful mathematically. It has been tested time after time, and it passes every test. It is probably the best tested and best verified theory in modern physics. But it had a big problem, which Einstein really struggled over, and that was that if the universe is static and unchanging and eternal, which is an idea that sort of goes back to Aristotle, but matter curves space, and that curvature of space causes matter to sort of move along the lines of curvature and clump together, then why doesn't the universe collapse in on itself? And that was a big problem that people attempted to solve in different ways. Einstein solved it by putting a fudge factor into his equations of general relativity, which became known as the cosmological constant. I'll get back to that in a minute. But in 1922, a Russian mathematician by the name of Alexander Friedmann produced a whole range of model universes that were not static, that were instead moving. And he showed that you could self-consistently solve these equations for universes that would have changes in scale with time. They could shrink, they could expand, they could more or less do anything you want, and you didn't need a cosmological constant in an expanding universe to avoid the collapse. Now, he died of a bacterial infection, food poisoning, in the early 1920s, and if he had not died, he might have actually accomplished much of what Lemaître accomplished. He was in post-revolutionary Russia and was a little bit isolated, but we'll never really know what Alexander Friedmann could have done had he not passed away as a young man. Now, another pioneer, Wilhelm de Sitter, who's shown in the picture on the right with Albert Einstein, attempted to solve the collapsing universe problem by having a universe that had no matter in it at all. If you have no matter, then it's not going to collapse. Now, that sounds a little academic, but actually, our universe is pretty dilute in terms of the amount of matter that's in it. And even though space is curved, it's not curved very much. So it was not too bad an approximation. And he actually showed that if you put 2 points of matter, 2 galaxies into a solution, that they would sort of move apart from each other. So that was the de Sitter dilute universe model. And all of these things were solutions to the equations of general relativity, which can be written very compactly in the form that you see up there. So there are 3 terms. Each of those terms has 2 little subscripts, and those little subscripts tell you that they are actually not single values, but matrices, sort of 2-dimensional lists of numbers. And so this is really a set of matrix of equations. And the big G term on the left expresses how space is curved. The T term on the right tells you what the effect of matter and energy is on that curvature. And the little lambda factor in the middle with the small g is the fudge factor, the cosmological constant that provides a repulsion. And what that equation essentially tells you, and this is sort of a famous way of describing it, is that the curvature of space tells matter, and light for that matter, how to move, and matter tells space how to curve. And that's basically what that equation says. And the way you solve those equations is you assume some geometry of space called a metric, which describes the relationship between different points in space, their distances. And if you allow that metric to change with time, if you allow space to expand or contract, then you have the kinds of solutions that Alexander Friedmann came up with. Now, Lemaître came along at this time, and he had not read any of Friedmann's work. Friedmann's work did not really make it out of Russia for a decade or so. And so he kind of started from scratch. And he wrote a thesis in 1925. The cover page of that, you see, you can get the whole thesis from MIT online. He didn't know how to spell Massachusetts, but otherwise he was brilliant. But what he did was he put together a metric that was time variable, and it was kind of a hybrid between Einstein's sort of matter-filled universe and de Sitter's matter-empty universe. And it was time-dependent. So at early times, it was like the Einstein universe, and at later times, it was like the de Sitter universe. And he showed that this was a perfectly consistent solution of the equations of general relativity, and that the curvature of space decreased with time. So this was an expanding universe model. He didn't require a cosmological constant. And the difference between what he did and what Friedman did is that he, Lemaître, had access to the data. He was at Harvard College Observatory. And at the time he did this, astronomers were finally determining the distances to galaxies and discovering that galaxies were moving apart from each other. And so what Lemaître then did was to derive certain consequences of his model, which I'm going to tell you a little bit about later. So if you go to general relativity textbooks, you see the name for the metric in various forms. The full name is the Friedman-Lemaître-Robinson-Walker metric, because Robinson and Walker a decade later showed that you could derive this in a somewhat different way. Sometimes it's just the Friedman, sometimes it's just the Friedman-Robinson, depends on the textbook. But Lemaître definitely did this work, and he did it in the mid-1920s. So around that time, distances to galaxies were finally determined, and the trick to doing that was to use something that we call the cosmic distance ladder in astronomy, where you determine first the size of the solar system, size of the orbits from certain observations, ultimately the transit of Venus a long time ago. Then you learn the distance to the nearest stars by using a technique called parallax, where you look at the sky in the spring and then you look at the sky in the fall when the Earth is fully on the other side of its orbit, and the nearest stars, at least through a telescope, will seem to move in angle more than the distant stars. And by knowing the diameter of the Earth's orbit, you have the distance to the stars. And then from there on to the cosmic distance ladder, there are variable stars called Cepheid variables, which pulsate. And by measuring the distances to those stars in our galaxy, early astronomers, including Henrietta Leavitt at Harvard, determined that the period of the oscillation and the intrinsic brightness of the star are related to each other very, very tightly. So by determining the period of the pulsation, you knew the distance. And that you could do in the nearest galaxies, and that's what Edwin Hubble and his colleagues did, because they found a Cepheid variable in the Andromeda galaxy, marked up there VAR exclamation point in his photographic plate, and all of a sudden he knew the distance to Andromeda, and then other galaxies. And then you could calibrate even more distant galaxies by looking at supernovas, because they have a definite brightness curve. And so essentially much of the universe could be calibrated in that way. And at the same time, other astronomers were looking at the color of light, the spectrum of light coming from galaxies. And it was observed that galaxies, pretty much from a chemical composition point of view, the spectrum of light, the bumps and wiggles as a function of frequency, tell you the chemical composition. And galaxies are made of stars, and more or less stars are all the same composition, give or take, for this lecture. So what was curious, though, is that the pattern of dips and peaks in the spectra were shifted more and more to the red the farther away the galaxy was. And so it was inferred that there was some process that made galaxies move faster away from us the farther away they were. And that velocity-distance relationship was interpreted in all sorts of different ways, but it was certainly credited, this relationship, it was credited to Edwin Hubble himself, who, along with some other astronomers, had made the distance observations, and others like Vesto Slipher, who made the velocity observations. The result of all of these observations is that that relationship between distance and recession velocity was actually linear. It was the equation of a straight line. So the speed of a galaxy away from us is equal to the distance to the galaxy multiplied by a constant called the Hubble constant, named after him. And the equation itself is traditionally called Hubble's law, based on all this work. Now, Vesto Slipher didn't get credit, and Milton Humason didn't get credit, and so on and so forth. But this is called the Hubble relationship, and it was published by Edwin Hubble in 1929. However, in 1927, Georges Lemaître published the same relationship before Hubble did. And he actually published it based upon his solutions to the theory of general relativity. It came out of the metric that he had written down and used to solve for this expanding universe. And he published this in 1927, but he published it in French in a Belgian journal. Now, the internet did not exist at that time, of course, and so you got your scientific journals shipped in a brown paper wrapper, sometimes months after they were published. And in fact, very few astronomers actually read the Annals of the Scientific Society of Brussels. And fewer of them read French. French was not the language of astronomy. So this paper was more or less ignored. But what was interesting is that not only did Lemaître derive from general relativity this linear relationship between the galaxy recession velocity and the distance, he actually interpreted it correctly. Because when you learn about this in a class, as a student, the immediate thing you think of is there's this big volume of space, and galaxies are flying through that volume, and they're flying through it like the shrapnel from an explosion. But that is not actually what's happening, and Lemaître understood that. What's actually happening is that space is expanding, and galaxies are caught in that expansion, and so they're just expanding along with the rest of space. And so the question then is, well, why is there a redshift if these galaxies are just part of the general expansion of space and not moving relative to fixed points in space? And the answer can be understood with a very simple analogy that is very imprecise but is still useful. So we live in a three spatial dimension universe, but imagine for a moment that we live in a two spatial dimension universe, sort of like flatland. And we represent that two dimensions by the surface of a balloon. So the third dimension in and out of the balloon does not exist. All of reality is that two-dimensional surface on the balloon, which, by the way, is finite, but it's unbounded. You can keep going around and around, and you never reach a boundary because you can't go up and down. But imagine drawing on that a little squiggle that represents the wavelength of light being emitted by a distant galaxy on the left side near my thumb. And that light is being emitted toward the galaxy on the right. Maybe that galaxy on the right is us. When the light is emitted from a distant galaxy, the universe is one size. When the light is received from us, if it's a galaxy billions of light years away, the universe is expanded during that time. And so the wavelength of light is actually stretched in the fabric of space. And so if you compare the wavelength when the light is emitted to the wavelength when the light is received on the Earth, lo and behold, it's redshifted. And if you actually take a ruler and do this on a balloon and measure these distances as you're blowing the balloon up, you see that there's actually a linear relationship between the distance and, if you inflate the balloon at a constant rate, the rate at which these two dots are moving away from each other. And so that is the correct interpretation of the redshift, called the cosmological redshift. There were all sorts of other ideas, like light just got more tired, it lost energy as it moved through space, all sorts of other things. None of that was right. It was that the space is expanding and galaxies or clusters of galaxies are caught in the flow of that expansion. So Lemaître was ignored, but even worse than that, in 1929, his former mentor, Arthur Eddington, republished Lemaître's solution to the equations of general relativity without crediting him. And when this was pointed out to Lemaître, there's Eddington on the left, a student pointed this out to him. Lemaître immediately wrote to his former mentor and wrote rather elegantly. Instead of saying, you SOB, what did you do? He said, "Dear Professor Eddington, And Eddington, after reading the letter, immediately recognized that he had simply forgotten that he had read the paper that Lemaître had written in the French journal, and that happens to all of us. I have a colleague who says to me that he's republished every 10 years by people who either didn't read or forgot they read the paper. And Eddington actually went a step further. He said to his former student that this paper has to be published in English. It has to be translated into English. Oh, let's see here. We are stuck. There we go. Come on. You can do it. Come on. There we go. Okay, now we're unstuck. So Eddington arranged to have the paper translated and published in the monthly notices of the Royal Astronomical Society, a very distinguished British journal written in English, read by lots of astronomers. And there is the title, exactly as it was in French, by Abbé Georges Lemaître, because he was a priest. That was the honorific title, even though he was also a professor. The only problem is that this paper had one defect, which was the key portion of the 1927 French version that included the relationship, what was called the Hubble relationship, was actually missing from the English translation. And so if you look at the French version, you see very, very clearly that Lemaître really did derive that relationship. After he shows his solution to general relativity equations, he then takes data he then writes out the relationship, the linear relationship, and then he derives the Hubble constant. He says, using the 42 nebulas, those were the galaxies, from the list of Hubble and Stromberg, and taking account of the proper motion of the sun, because you have to take that out, one finds a mean distance of 0.95 million parsecs. That's a unit of astronomical distance, about 3 light years. And a radial velocity, that's the recessional velocity, of 600 kilometers per second, and therefore the constant is 625 kilometers per second per megaparsec. That's not the value we know today, but that's the Hubble constant, and that was published 2 years before Hubble. So, why don't we credit Lemaître? And the answer was really the subject of sort of conspiratorial speculation until 2011, when Mario Livio, who's an astronomer at Space Telescope Science Institute, dug through the files of the Royal Astronomical Society, which publishes MNRAS, and lo and behold, he found that Lemaître had done the translation himself and deleted the paragraph himself. And in his cover letter to the editor of MNRAS, a guy appropriately named Smart, probably not related to Maxwell Smart if you like this series, he wrote that I sent you a translation of the paper. I did not find it advisable to reprint the provisional discussion of radial velocities, which is clearly of no current interest, because by the time this paper was published in 1930, there was so much more data that the number that Lemaître came up with was out of date, but the relationship was not out of date. So this makes Lemaître look like some kind of scientific saint, because most of us would want to include the thing that had become the most famous. And so it's sort of a mystery as to why Lemaître would do this. Maybe he really was a saint. Maybe he was just very modest. Maybe he was just a really good scientist and recognized that the data he had used to derive the numerical number, remember the relationship came from his metric, was obsolete. But actually about 10 years or 6 years ago, very mysteriously, Simon Mitton, who was an editor at Cambridge, found another letter, and this was from Smart to Lemaître, saying, I'm looking forward to your translation. And in that letter, the editor says, please don't include the part about the radial velocities. And why he did that, we do not know. We will never know. But in any event, Lemaître lost the opportunity to become associated with the most famous relationship in astrophysics, the Hubble law. So, nonetheless, there's even more irony to this, because even though Edwin Hubble gets credit, Edwin Hubble never believed in the expansion of the universe. He thought that the light was getting redder in more distant galaxies because of light fatigue. And in fact, you can find from the LA Times in 1941 a little snippet. It's a sort of a science roundup, which begins with Savant, which was Hubble, brilliant guy, refutes the theory of the exploding universe. And that the world's largest telescope shows that the universe is not exploding, but is a quiet, peaceful place, and possibly just about infinite in size. So when you read in a book that Edwin Hubble was the one who discovered the expanding universe, that isn't quite right. So, I mean, he's very deserving. You know, he's a famous, great astronomer, but he just should not be credited with that. So about a year later, Lemaître gets into an argument with Eddington about whether this expanding universe implied a finite beginning in time. And Eddington said, no, it didn't. And Lemaître said it really had to, because trying to make the universe infinite as you go back in time required a very ad hoc solution to the equations of relativity. And so Lemaître published a short letter in Nature in 1931, thankfully in English this time, in which he publishes the idea that the universe had a finite beginning, that the physical state of that universe was very, very different from the state that we have today. He called that the primeval atom model. And if you read this, it's a beautiful 4-paragraph description of a universe that begins in actually a quantum state, in his case, a sort of single primeval atom, and then suddenly explodes and expands, space expands, and becomes the universe we know today. Pretty much everyone credits Lemaître with the idea of a Big Bang, even though he doesn't call it the Big Bang. That was a pejorative term used by Fred Hoyle a couple of decades later, who didn't like the idea. But Stephen Hawking says that Lemaître was the first to investigate the origin of the universe that we now call the Big Bang. And John Farrell, in a biography of Lemaître, points out that Lemaître, who is not a quantum physicist, argues in this paper that at some level space and time had to be quantized. So it's a very interesting and sort of prescient paper, which I would recommend getting online. I'm not going to read this here. And that was it. He became the father of the Big Bang. Father Lemaître became the father of the Big Bang. But the battle for his reputation was actually not over, because as soon as this was published, there began to be questions about whether the fact that he was a Catholic priest played some role in his asserting that the universe had a finite beginning. And World War II came along. He was trapped in Belgium. He actually was nearly killed by an Allied bombing run that was supposed to hit the train station nearby. The Nazis were there, but actually hit the university. But he survived. And after World War II, this controversy came up again. So in the late 1940s, 3 other physicists, Tommy Gold, Herman Bondi, and famous astrophysicist Fred Hoyle, came up with an idea for a counter to the Big Bang model, simply on the basis that they didn't like the idea that the universe had a finite beginning. But they also knew that galaxies were expanding, space was expanding, and if you had a universe that had no beginning, that was infinite in time, how do you avoid the universe being essentially devoid of matter, having a separation between the existing galaxies that would be infinite? It was infinitely dilute. So their idea was that maybe matter was being created in violation of the conservation of matter and energy, just being created a little bit at a time. And given the expansion rate of the universe, all you had to do was to have a couple of hydrogen atoms per cubic centimeter formed per century. No one's ever going to notice that. Very small. I mean, you know, just a little error. And Tommy Gold, by the way, went on to found the modern Department of Astronomy, where I taught for 13 years and was very famous there. And Fred Hoyle was not only a superb astrophysicist, but a sort of a Carl Sagan of his time. He had his own radio show on the BBC, and he lampooned the idea of the primeval atom model by calling it the Big Bang and calling Lemaître that Big Bang man. And he would do that at various conferences, and that was much to the annoyance of Lemaître. But the idea that Lemaître had come up with this idea because of his religious inclinations and background was actually given a significant amount of credence by a talk that the Pope in 1951 gave to the Pontifical Academy of Sciences in Rome. It's a very famous speech. It's called the Fiat Lux speech, Let There Be Light. And in that speech, the Pope says that present-day science, with one sweep back across the centuries, has succeeded in bearing witness to the august instant of the primordial Fiat Lux. It has confirmed the contingency of the universe. Hence, creation took place. We say, therefore, there is a creator. Therefore, God exists. Boom. Now, Lemaître was in the audience, and he was really irritated by two things. One is suddenly his model had been given this religious taint. And the other was, and I kid you not, because he complained to one of his students afterwards, he was not recognized by the Pope in the audience as being the author of this model. So he was a human being like everyone else. But this was really bad because his scientific opponents like Fred Hoyle and George Gamow immediately began saying, well, that was it all along. It was just the Big Bang model was a disguise for trying to introduce the book of Genesis into astronomy. So Lemaître then found that the Pope was going to give the same speech to a much larger audience, the International Astronomical Union, the next year in Rome. And so Lemaître was so exercised that he traveled to the Vatican. He got the Vatican astronomers, the director of the Vatican Observatory, who was an advisor to the Pope, to get him into the Pope. And either he or the Vatican Observatory director, it's not quite clear which, talked the Pope into omitting that part of his speech, which he did omit. It was not given that way to the IAU. But nonetheless, the damage was done. And Lemaître more or less retreated from kind of going to meetings and talking about his model. He actually made many other contributions in numerical sciences. He had the first digital computer in Louvain installed. He did a number of papers on numerical methods and so forth. But about 2 weeks before he died of leukemia in 1966, he was informed by his friends that two radio engineers by the names of Penzias and Wilson had found with their new sensitive radio telescope in New Jersey that there was a uniform static that pervaded the cosmos. They thought it was pigeon poop, but once they cleaned all of that off, it was still there. And Lemaître immediately recognized that that background static had to have something to do with a transition in the state of the universe early in its history, and that the universe was not in steady state, that it did not go back infinitely in time, and that he was right. And to his credit, actually, Fred Hoyle realized that Lemaître was right and recanted the steady state model because of this discovery. So what is the cosmic microwave background radiation? Well, it's most easily understood by thinking about what happens when you look up in the sky and there's a uniform cloud. Okay, so that cloud doesn't allow you to see further on. And what that cloud is little droplets of water that are scattering the light so much that the light can't travel further up and out, or the light from out there can't travel in and get to you, so you cannot see the sky beyond the cloud. You can only see the surface of the cloud. And the cosmic microwave background radiation, this uniform static, is basically the same thing. It's the surface in the expansion of the universe at which the temperature of space becomes low enough that the space becomes transparent. So how does that work? Well, if the temperature is high enough, all of the particles in an atom, the electrons and then the nucleus, are separated from each other. So you have free electrons that are not bound to the atomic nuclei. They scatter light so well that you cannot actually, in this universe at this temperature see anything at all. Everything is an opaque, sort of uniform screen of scattered light. Temperature drops down to a point at which the electrons become bound to the atoms, and suddenly space is transparent. And that moment is a kind of a screen, like the base of a cloud, at which suddenly you can see through space. And that moment corresponds to a very high temperature, about 400,000 Kelvin. But that was 13 billion years ago. And so space has since expanded so much since then that that light has been stretched out, redshifted enough, that the apparent temperature that you see is only about 3 degrees above absolute zero. And that is the temperature that you get by measuring that static in the radio and thermal infrared part of the spectrum, about 2.7 degrees Kelvin. It's actually not entirely uniform. There are little areas that are hotter and colder by about 1,000th of a degree Kelvin, and they tell us maybe about the origin of the structure of the universe in these little bumps and wiggles. But Lemaître was vindicated. Okay, now, next part of the talk, I want to, let me just see how much time I have. Yep, about 15 minutes. So I want to just briefly, very briefly, talk about other things that Lemaître did in the 1930s before World War II, and then the battle with Hoyle and colleagues sort of put an end to his work. So first of all, I want to just say that what Lemaître did in his vision of the Big Bang wasn't quite right. It doesn't quite explain element formation. He thought that the Big Bang had a cold start, that the universe was cold at the beginning. It's important to note that in the 1940s and 50s, nuclear physicists took this model, and people like George Gamow and Hans Bethe and colleagues realized that this initial start had to be very, very hot, and that's what actually leads to element formation and the cosmic microwave background. But Lemaître did many other interesting things, and he played around with the expansion rate of the universe. So here's an unpublished figure of his that was found in the archives at his university in Louvain, and it shows different versions of the history of the universe. Some of them expand and then they collapse back on themselves. Others expand forever at a uniform rate, and others accelerate in their expansion. Those are the ones at the top. And if you look at a modern figure that shows data comparing modern cosmology models with distance data to supernovae, those look the same. Those are the same models we're considering today. And the data from supernova that give you the distance to the receding velocities actually tell us that the expansion of the universe was initially constant and now seems to be accelerating. So Lemaître thought about some of this stuff pretty early on. Lemaître also sort of intuited the idea of inflation. So one of the characteristics of our universe is it seems very flat and relatively homogeneous. These temperature bumps are very, very small compared to what they could have been. And one way to have that happen is to have the initial expansion of the universe be very, very rapid. In fact, almost non-physically rapid. And so this very, very early, very, very short epoch is called cosmic inflation. And right now astronomers are trying to detect the echoes of that. Haven't quite done it yet, but they're at it. Actually, Lemaître presaged this idea. He played around with a model with a variable cosmological constant in which he starts out with a universe that begins at infinite speed, that's inflation, then it slows down, and then it starts expanding, accelerating in its expansion again. And that's kind of like the universe we know today. He did it that way because with the data he had from galaxies at the time, the age of the universe he derived from a uniformly expanding model was actually less than the age of the Earth. And he knew that couldn't be possible. The age of the Earth was being determined by geological methods at the time. And so he had to adjust his cosmology model so that the universe would be older than the age of the Earth. But a more interesting thing that he did, and maybe more significant, is that he also presaged the idea of dark energy. So dark energy is some sort of property of expanding space which is causing that expansion to accelerate. And we see that in the supernova data today. It's not understood what it is, but it's thought to be a sort of a non-zero vacuum energy to the space itself, causing space to expand. As the universe gets larger and larger, matter becomes more dilute, the dark energy becomes more important. Well, Lemaître published this in the 1930s. He took the equation of general relativity that you see here. There's the cosmological constant in the middle. And he said, what would it be if we took that cosmological constant and put it on the right-hand side of the equation and made it a vacuum energy? And he wrote this up in the Proceedings of the National Academy of Sciences in 1933. Again, thankfully, a journal everyone read in English. And he wrote in that if you take the cosmological constant and put it on the right-hand side where the matter-energy tensor is, it becomes a vacuum energy. And he says this is essentially the meaning of the cosmological constant. That's a typo. It should be cosmological, which corresponds to a negative density of the vacuum. And then he writes out the value. And Robert Kirshner, who's an astronomer writing in physics today, said Lemaître's interpretation is almost shockingly modern. That is more or less what we say today about the origin of the accelerating universe. So Lemaître did many things, and at the end I'll recap some of what he did, but I want to now turn to his thoughts on the questions of time, creation, and God. I'm going to skip the ones about time because I don't have time for it, but I want to show you a couple of interesting things about his writings. So first, there's an early version of his letter to nature that's in the archives in Louvain. And that manuscript version actually has an extra paragraph at the end of it. So he talks about the universe expanding. He talks about the initial quantum state and how different it would be from the present. And then in the bottom, in a paragraph that's actually crossed out in pen, he writes, I think that everyone who believes in a supreme being supporting every being and every acting, presumably action, believes also that God is essentially hidden and may be glad to see how present physics provides a veil hiding the creation. Now that is not in the published version, and he presumably didn't submit it that way because he crossed it off with a pen. But it's clear that he's pondering this. And the whole question of how God expresses himself through his creation is kind of embodied in that paragraph, that God doesn't act in the way that a super being would act by doing mysterious and magical things, but actually acts through the physical laws that we learn about through our scientific experiments and observations. From a Thomistic point of view, which a famous philosopher, theologian, Thomas Aquinas, we are the instrumental or the efficient causes, and God is the first cause. But God does not intervene. God acts through the efficient or instrumental causes. Lemaître also pondered what it really meant to have a beginning of the universe. He said, we may speak of the Big Bang as of a beginning. I do not say a creation. That is, that's not when the universe first didn't exist and then did exist. He recognized that there's a difference between that and the question of something having no existence whatsoever and then coming into existence. And again, from the Thomistic point of view, St. Thomas would say that the beginning of the history of the universe, he actually didn't think the universe had a beginning. He sided with Aristotle. But he said that God, the creation, is God simply keeping everything in existence at every moment in a sort of a timeless way, that this radical relationship of everything that is part of reality to God is what keeps everything in existence. That's creation. The beginning of the history of the present universe is the Big Bang. And Lemaître essentially agreed with that. He's quoted as saying, and it's not quite clear where he said this, that the question of whether the Big Bang was really a beginning or rather creation is a philosophical question which cannot be settled by physical or astronomical considerations. So he thought carefully about these kinds of things. He was also very much opposed to the idea of trying to read into the Bible sort of insights that we have today from modern science. And of course, he also didn't think that we should be guided in our science by what's in the Bible. So the first of those is sometimes called concordism, and he was very much against that. And one of his quotes in this regard is, he talks about the fact that the doctrine of the Trinity is much more abstruse than anything in relativity or quantum mechanics, but it's necessary for salvation, and so it's stated in the Bible. If the theory of relativity had also been necessary for salvation, it would have been revealed to St. Paul or to Moses. And so they didn't have secret knowledge. They were not Gnostic. And that's very important, because sometimes people try to read modern science into the Bible, which makes no sense, because the science of today is not going to be the same as the science of 1,000 years ago, and it wasn't of the science 200 years ago when we thought that the universe was a Newtonian clock. And so, that is not what the Bible is for. The Bible is to teach us the salvation history of humankind. The most interesting speculation that he made was on the comprehensibility of the cosmos. And this was a question that came up for both Lemaître and Einstein, who are shown here at the Athenaeum at Caltech in around early 1930s. And I'll show you what Einstein had to say in a moment. But what Lemaître had to say was that the natural truth, which is the second paragraph here, which is the understanding of the universe through its physical laws, is precisely proportioned to the faculties of our intellective nature. It is humanity's task to understand and value the creation that surrounds it and to which it belongs, to perceive in it a reflection of the divine intelligence by marveling at being surrounded by matter that is intelligible. Not that matter that is intelligent, but is understandable, intelligible. And that was a response to this question of why the universe should be comprehensible at all. And then, of course, he talks about the supernatural truth, which is the salvation history revealed in the Bible. Einstein had much the same concern. He approached it in a different way. He's quoted as saying that the great mystery of the universe is its comprehensibility. But he elaborates on this in a 1952 letter to his friend, the mathematician Maurice Solovine. He says, "You find it strange that I consider the comprehensibility of the world as a miracle or as an eternal mystery. Well, a priori, one should expect a chaotic world that cannot be grasped by the mind in any way. And one could expect the world to be subjected to law only to the extent that we order it through our intelligence. Ordering of this kind would be like the words of a language, the alphabetical rules of a language." But by contrast, Einstein goes on to say the kind of order created, for example, by Newton's theory of gravitation — he was very humble, he didn't offer his own theory in this case — is wholly different. Even if the axioms of the theory are proposed by man, the success of such a project presupposes a high degree of ordering of the objective world, and this could not be expected a priori. This is the miracle which is being constantly reinforced as our knowledge expands. And in fact, one of the curious things about this universe is that it had to start out with a very high degree of order relative to other kinds of alternative universes that we can think of in our minds. Now, maybe that means that we're one universe out of an enormous number of universes in a multiverse, and the one that we can exist in and contemplate is the one that's most highly ordered, and that's sort of popular with cosmologists today. But it's still a mystery that it is so highly ordered, and it's a mystery that we can understand and comprehend it. And Einstein, in the final paragraph, goes after what he calls professional atheists who don't bother to really think about how unusual and mysterious this really is. So then Lemaître talks about pursuing two paths, science and religion. He says that he has pursued both. Nothing in his working life, nothing he's ever learned in his studies of either religion or science has caused him to change his opinion. He has no conflict to reconcile. Science has not shaken my faith in religion, and religion has never caused me to question the conclusions I reach by scientific methods. And this is a quote that I give to students who ask, can I continue to pursue my faith and be a scientist? And one of the most brilliant scientists of the 20th century, having found no conflict at all in this, I think is a very important guide for anyone who would have such doubts. So let me close with Lemaître's legacy, and I'm now just about out of time, so that's about right. if you list the things that Lemaître did in this miraculous decade of the late 20s to late 30s, mid-30s, there were an amazing number of things that he worked on, and the top three were kind of the most important. The Big Bang, which is the top one. The interpretation of the cosmological constant of Einstein as an energy of the quantum vacuum. That's the way it's thought of today by modern physicists. And he also, and this was pointed out by Saul Tucholsky at Cornell University, in his PhD thesis, he actually took the solutions that a scientist named Schwarzschild had put together, which we now recognize as a black hole. He put them in the right coordinate transformation to make a black hole a black hole. So what Schwarzschild did was he showed that if you have extreme gravity, extreme concentration, you get a physical singularity. But his singularity was actually sort of at the edge of his solution, not at the center, which is what we think of as a black hole. And Lemaître did a coordinate transformation and showed you could put the singularity at the center. And so he essentially fixed Schwarzschild's solution, and he's just not recognized for that today, but it's in his PhD thesis. So the accolades for Lemaître in the last 10 years have come from the recognition of what he really did and the fact that he simply was unrecognized in his own time. Peebles, who won the Nobel Prize in 2019 for his contributions to cosmology, said that the demonstration that our physical universe expanded from a very different state grew out of advances that to a striking degree were the work of a single person, Georges Lemaître. And then Simon Minton in his biography says that Lemaître was arguably the greatest cosmologist of his generation. So in 2018, the International Astronomical Union was presented with a proposition to rename the Hubble law as the Hubble-Lemaître law, and it passed by about 70%. It was quite a large number. Now, after this passed, at least one very prominent cosmologist, Michael Turner, said to me, I'm not going to call it the Hubble-Lemaître law. That's too long. I'm just going to keep calling it the Hubble law. And of course, the IAU has no legal power over this sort of thing. So astronomers have to do what they have to do, but at least in Wikipedia, they recognize that it's the Hubble-Lemaître law. So Lemaître was a remarkable scientist, a faithful Catholic, a recognized priest. He was named a Monsignor, a prelate of the papal household. And he really thought deeply about the relationship between science and faith. And so in accepting the Franck Prize in 1934, he said in his speech that science is beautiful, it deserves to be loved for itself as it is a reflection of God's creative thought. And Lemaître was one of those people who illuminated to all the rest of us just what that thought really was. Thank you.